This video is going to go into a bit about IP addresses and subnets and try and demystify them a little bit. Previous videos I have talked about what they are and how they work, but they still can be a little bit confusing to sort of wrap your head around, but they are really essential for understanding networking and how certain networking concepts work, like routing and VLANs and that kind of stuff. So with every IP address, you have really two numbers that are required in order for it to make sense. You have the IP address itself, which is made up of 4 binary numbers, and you have the net mask, which is also made up of 4 binary numbers. And you can see that each number that corresponds with the IP address has also a corresponding number for the net mask for that particular number. So you can consider this to be 4 numbers that each have their own corresponding number for the net mask. So one thing that can help you to understand how this system works is to link it back towards actual addressing. So what we have here is the address for the Clearwater campus of SPC. But for this example, it doesn't really matter. We're going to just look at the addressing and how they relate to each other. So as you can see here, addresses are made up of several different pieces of information. You have the building number, the street that building number resides on, and the area that street resides on. And this is somewhat similar to how IP addressing and net masking works. So you can imagine that, say you're a mailman and you have a letter that you're going to send to this address. There's several different ways you can interpret this address, but one way you can interpret it is that this number here is the number on this street here that you're sending it to. So you have 2 separate pieces of information. You have the number of the building number of where that letter is supposed to go, and the address of where you can find that building number. So your address here can have several different numbers associated with it. So you can imagine this would be the street, this would be Drew Street, for example. This entire address here is referencing this road. So this road here, this address here is what eventually leads to this road. And on this road there can be multiple different addresses. In this case, you can say that this address here belongs to this building here. You can say that's SPC. And then you have 2466, like here, 2467, and so on and so forth. So one sort of important conceptual question to ask yourself is, how did we know that this was the building address and this was the street address? How did we know that? How did we actually know that this number corresponded to a building? Well, just as humans, we sort of already know this, that, you know, we're so used to addressing how it works that we know that looking at this address that this is a building number and this is a street. But if you're talking to a computer wouldn't know this. It wouldn't know where to draw the line. A computer might consider that, you know, if a computer was to look at this, it might say that this whole part here was the building number and the rest of this was the address. But you can see that's not correct. And if you tried to send a letter to this, you know, you could do that as a human, but as a computer, it would get very confused because there are multiple buildings that are either not being accounted for. But either way, this address does not accurately represent what this model is showing. So going back to our previous example, we could consider this entire this top number here, the IP address, as being the equivalent of this entire address here. So you could look at this and say, you know, as a human, and say, okay, I want to send a packet to this address. How are you going to find it? Well, it's not like this address where we know how they look and what to look for in terms of building numbers and street numbers, city and state. All we have are these numbers to go on. How do we know where to send it? And that's the purpose of the network mask. The network mask tells whatever system's looking at this what part of this address belongs to the host and or the building, or what part belongs to the street. So we can consider, for example, in this particular example, we have all 255s in this on these 3 digits. So these 3 digits would be considered to be the street address. So that would be the same as this, and that would lead to the street. Whereas this part, as you can see, has all zeros down here, so that would correspond to the building address. So going back to how computers would see this, we have an example here. So I have 192.168.0.2 with a net mask of 3 255s and then 0 after that. And over here I have almost the same address, but not quite the same address, 192.168.0.2. So almost the same as this first one here, but you can see that this digit here and this digit here have been changed. And because the subnet mask tells the machines, the routers and the computers, what part of this address belongs to the network and what part belongs to the host, you can see here that we can divide both of these like this. In this part we would have the host address, and the rest of this would be the network address. So even though these two network addresses are very similar to each other, they're not the same. So this would be equivalent of, like, you have a letter that you're sending to another street that has almost the same name as your street does. That's kind of what's happening here. You have your computer here, instead of this computer, sending a packet to this computer. Well, it's looking at the destination, the source and the destination. The source is being like the return address on a letter, and it's putting this number into that return address, and then the destination address being this number. And even though they're only off by 1, that's enough for the computer and router to know that this is trying to go to a different network. But one aspect that I've shown, that I haven't shown yet, is that this subnet mask can be various different lengths. So this is, the number is telling, again, the machine which part of that address is like the street address and what part is the house number. But we can make that pretty arbitrary. We can make that, we can change that up. So I can say that instead of it like being like this, I will say that it's like this. So now it's, the subnet mask is 255.255 and then all zeros after that. And the zeros are important. The zeros are what tell the computer what part of this address belongs to the street or network and what part belongs to the house number or the host. So in this case, the side with 255s is going to be the network, and the side with zeros is going to be the host. So it would be split down the middle like this. So now if a machine was trying to send or receive data, it would have to reference this network number when it's trying to either send or receive data. But now we've changed it up a bit. Now instead of having a maximum of 255, or rather 256 minus 2 possible addresses like this, let's just say it's 256, because that's the maximum range of a binary number, is 256 unique values. Generally it goes from 0 to 255. In an actual network it's this minus 2, because 2 are reserved for other things, but let's not get into that yet. Let's just say that because we have one available binary digit to tell the machines what part is the host, or which part is the host and which part is the network, we can have up to 256 hosts or 256 buildings on that street. Over here, because we've changed this, now these two numbers are associated with the host address or the street, the building number, whereas this part here is considered to still be the network address, or the street that those buildings would be on. But now, since we've expanded this out so much, instead of having 256, we now have 65,000 approximately possible host addresses. So there can be, on this one street here, up to a little over 65,000 different buildings or host computers. But a side effect from doing that is we've reduced the size of our address, our network name, or our network address. So the number of streets that we can have gotten smaller, but we've increased the size of the number of buildings or hosts that we can have on those streets. So another thing that can help is to expand it out into its full binary form, because this is how the computer interprets it. We interpret it as base 10 numbers like this, but computers don't have that. They only have base 2, so it's either on or off. So you have your IP address up here, 192.168.0.1, and that boils down to these numbers in binary. So you can see that there's 8 binary digits per number. And below that you have the subnet mask, which is 255, 255, 255, and 0. And if you notice here, all of these bits here are turned on. So when your computer goes to figure out which part of this address belongs to the network and which part belongs to the host, it uses this number here, comparing these bytes or these bits and these numbers, and from that it's able to figure out which part belongs to the network and which part to the host. If I want to change this up like I did before and make this into a 0, then I have to also change all of these bits down here, these 8 bits. Oops, forgot one. So 8 zeros at that point. And again, it's comparing these bits together to figure out which part belongs to the address for the network and which part belongs to the host. In this case, this part here would belong to the network, this part would belong to the host. I can do the same again. I can take this, make this a 0, and make all these zeros also. So one interesting thing to note though, and one general property for subnet masks, is that the subnet mask will always go from 1s to 0s. It will never go from 0s to 1s or have 1s and 0s intermixed. So on one side, it's always going to have a constant line of 1s and then switches to 0s, and from there it's just going to be 0s after that. So for example, I could say I want to make these 4 1s. Now that'll change this digit down here. So instead of it being 0, it will now be 240. But if I was to do that again, instead make this 241, I would then have to change this bit right here to a 1. And that violates the rules, because you can see here it's going from all 1s and switches to 0s and then goes back to 1 and then back to 0s. But the way that actually has to work is it has to go from all 1s and then switch to all 0s. It can't have 1s like intermixed like this. That's just not how it's able to work. And what that results in is that there is a set number. These digits here can only be certain values that correspond with this. So if I was to say, take this number here, make that into a 1, that now changes. It used to be 240, and now that changed it to 248, because that's the 8th place in binary. So we can actually calculate this for ourselves, what these numbers are going to be, what the set numbers are. And if you take a networking class, they probably will have you do this at some point, just to show that you understand how this works. So let's make it simple for right now. Let's just say that I'll erase this one octet, which is octet just means a single one of these digits. And I'm going to say our new network mask looks like this. So we have all 1s and then all 0s. So that means it's a good network mask. So what we can do here is try and figure out what this binary number is in its decimal form. So if you take in a networking class, they might have you do this. But you want to go, you would look at this binary number and start converting it into decimal using the decimal places of this number. So for binary, it goes 1, 2, 4, 8, 16, 32, 64, 128. So because the 128 place is the only one that's actually enabled, then we know that this has to be 128 as our subnet mask. But we could change that again and say that this 0 is actually also a 1. So in that case, we would do, again, 1, 2, 4, 8, 16, 32, 64, 128. So it'd be 128 plus 128 plus 64, which would be 192. And that's how we would derive our subnet mask number based on just binary number from the subnet mask. But that can still seem a bit confusing, and what this particular example is called is variable length subnet masking. A lot of times what you'll see are just entire octets of these that are just all set to ones and zeros. So a common thing is looking like this, where you have 5500. So entire digits in binary will just be either all on or all off, and that's what's considered to be the classing networking system. But going back to a previous point, this networking mask determines how many hosts are available on this network, and that's all done through these numbers here. And using these numbers, you can also determine how many hosts are available for a particular subnet mask. So because these are all ones and these are all zeros, that means that this network space is effectively cut right down the middle. So there are approximately 65,000 hosts and 65,000 possible network addresses. But that can be wasteful. If you don't have 65,000 computers to connect to one network, you don't really need to have all this. So by default, most likely, if you have a home router or whatever, almost always is going to have a default network mask of this, which means that the first 3 sets of binary digits refer to the network, and the last set belongs to the hosts. In this case, because you have one binary octet, one binary number associated with those hosts, you have all zeros to all ones as your range. And in binary, that means it goes from 0 to 255. So you may have a maximum of 256 unique hosts for this particular network. But if you want to, say, have maybe, let's say, 8,000 hosts, so you don't need 16,000, but you can't make do with just 256. You need to then adjust the subnet mask in a way that allows you to to reserve the number of hosts you need for a particular network, while also keeping the network address as large as possible. So there's a couple ways you can figure that out. One is to do it manually like this. Another way is to use a Subnet Calculator to figure out how many bits of the subnet mask you need to turn on and how many you need to turn off. Now to do this, we just need to keep turning bits off until we reach a certain number that allows us to reach our goal. So in this case, we said we want to have 8,000 hosts. So we know that 256 hosts is not going to be enough. So all of these are on. One shortcut you can do is you can consider that every time you turn a bit from 1 to 0 in this situation, you're effectively doubling the amount of address space on this side. So if I take this bit and turn it off, now instead of having 255 or 256 hosts, I now have 512 hosts. So it's still not enough. So we've got to keep going back and back. And in this case, we need to go back until, let's see if my math is correct. I want to say it's probably about here. So that would be 1, 2, 4, 16. So yeah, that would give us 8,191 hosts. So we've gone over the amount that we wanted to, but in this case, that's kind of we have to deal with, because we just don't have enough address. We can't evenly divide 8,000 into this system. So in this case, this number would now turn into 224, I believe. This would be 0. So this setup would give us our 8,000 hosts, a little bit more than that, but would also allow us to preserve a lot of our networking space here. So if we want to have multiple networks, we can say, you know, I want to have another network that's 169, for example, and that's a different network associated from this one. But another way to do it is through a subnet calculator like this one here. So right here we have a subnet calculator, and its job is to do basically the same thing that we were doing manually, but makes it a lot easier to figure out if you have certain requirements for the amount of hosts that you need. You can just input that into this calculator, and it will help you figure it out. So let's say we want to have, same as before, we want to have 8,000 hosts. So we need to switch it over to at least a Class B network, which you can see has changed the address here, which gets into the address classes, but that's sort of a different thing altogether. But you can see here it has the host per subnet. We click on that, and we have 8190 is the closest that we can get to the amount of hosts that we need for our network. So you can see here it changed our subnet mask to 255, 255, 224, 0, and it's given us the subnet bitmap down here, which correlates to what we would have to do otherwise. So you can see here that the 3 bits are set while the others are all 0. And in this situation, what we could do is we could take the remaining bits that we've set left on and use those for other networks, and we can further divide those down into more subnets. And the whole idea behind this is just to more efficiently use IP address space because it is limited. But a calculator like this can help you, at the very minimum, check your math when it comes to figuring out what kind of subnets you need and what kind of address spacing you need to program into this to get a certain amount of hosts.